Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So, welcome to the fourth lecture of dynamic programming playlist. What is the problem? Today's problem is going to be maximum sum of non-adjacent elements. Again, one kind of 1D that we will be solving. I'll be following the same pattern. You might have solved this problem previously, but the way I'll be teaching you will be something very different. So please do watch the video till the end to understand all the logic. Don't think that if you understand memoization it's done. You have to understand tabulation, you have to understand space optimization in order to be the best. Okay, so let's understand the question. Basically it states you will be given an array of n integers. That means you're given an array which consists of n integers. Okay, so you're supposed to return the maximum sum of the subsequence. Now remember, you have to pick up a subsequence which gives you a maximum sum, but there is a constraint. In the subsequence, none of the elements can be adjacent from the array. Okay, so for an example, if I look on this test case, which is 1 to 4, you can't pick something like 1 comma 2, or you can't pick something like 2 comma 4 because they are adjacent. Got it? So probably you can pick something like 1 and 4, which gives you the maximum sum 5. That's what the maximum sum will be. Like over here, you can't pick something like 4 and 9 together. You have to pick one of them. So probably I'll pick 9 and then I'll pick 2 to get the maximum sum as 11. So you'll be given an array and you'll be given the size of the array. You have to tell me what is the maximum sum that you can pick by picking up no adjacent elements in that subsequence. So what's the first thing that comes to your brain when you hear about this problem? It comes key, let's try out all subsequences. Okay, so that is something which comes to my brain is let's try out all subsequences with the given constraint. That's something which comes to my brain. And out of all these subsequences, let's pick the one with the maximum sum. Correct? Like we're gonna try out all subsequences, and whichever subsequences gives you the maximum sum, we're gonna pick that one. As simple as that. Now the question arises, whenever we say trying out all stuff, what comes to your brain? Obviously one thing comes to your brain, which is recursion. So we're gonna try out recursion, correct? And after that we are gonna see if there are overlapping subproblems, and that's for the remaining part. But we have understood that why recursion, because if they're asking you to try out all subsequences, we have to, and that is only doable by recursion. So how do you print all subsequences? That's a big question. Before solving this question, how do you print all subsequences? So there's a technique which is known as pick and non-pick. Okay, so I have taught this entire technique in lecture 6 of recursion series and lecture 7 in depth. So if you haven't seen both of the lectures, pause it right now. Yes, I repeat, pause this video right now, go back to lecture 6 and lecture 7, understand the pick and non-pick, come back and then watch this video. If you don't watch lecture 6 and lecture 7, do not say me ki Striver did not teach well. Okay, so you have to know this logic of pick and non-pick. Okay, so I know how to write recurrence. What did I teach you? Express every recursion in terms of indexes. Okay, makes sense. Do stuffs on that index. Okay, do stuffs on that index. Then return the best that you can get. Return the best that you can get. That is something which I know. Now over here, what is the problem? Pick subsequence with no adjacent. Remember this, with no adjacent elements. So where do you pick subsequence from? You pick subsequence from an array, right? You pick subsequence from an array, and whenever there is an array, there has to be an index. So the first property has been satisfied, that I will have the recurrence based on the index. Okay, now there is a question, there's a constraint rather, with no adjacent. How do I deal with it? Because I know how to print all the subsequences, but now there's a constraint which states with no adjacent elements, right? So we want the maximum sum, correct? So can I say our recursion to define something like this? F of index states the maximum sum, like the maximum sum that you can get if you pick a subsequence from the index 0 till the index. Maximum sum that you can get by picking up a subsequence with no adjacent elements from 0 to index. Makes sense? So can I say this, that if I end up at index 0, if I end up at index 0, what will be the best thing that I can do? Like, there can be a lot of things, but as of now, let's keep this aside. Let's think of the other cases, because we know we are going to start from n minus 1. Now in recursion, we know in order to print subsequence, you have a pick which states key take this element into your subsequence. Pick says take this element into your subsequence. So if you take this element into your subsequence, the sum has to increase, and the sum will increase by a of index. Perfect. Now tell me one thing. Think on yourself. I'm saying do stuffs. You're saying, okay, what are the stuffs that I can do? I can say this particular index element will be a part of my subsequence. Or I can say, let's not take this, and I will go. So if I decide that I will not pick, then it will be a 0 plus. I decide that I will not take this, it will be a 0 plus. Okay. So on stuffs, I can say these are the stuffs that I can do. I can either take the element index into my subsequence, or I can say I will not take this into my subsequence. These are the couple of things that I can only do. Now tell me one thing. If you are picking up an index, yes, if you are picking up an index, what is the question stating? You cannot pick up an adjacent element. So will you go to the previous index which you generally did in 1D? Will you? Because if you go to the previous element, there will be a no option. Like, there will be no option of picking that because you have picked up the index. So you cannot pick up the index minus 1. So can I say you will not pick index minus 1? So can I directly go to index minus 2? Think on this. Make sense? Because if I am picking index, I cannot pick index minus 1 because the condition states no adjacent. So the transition, instead of going to index minus 1 and deciding what will we do for index minus 1, instead of that, what we do is we say go to index minus 2. Yes, go back to index minus 2 because index minus 1 cannot be. So this is how you can do. Now if I decide that I'm not going to pick, if I'm not picking an index, can I pick an index minus 1? Makes sense. So I will say, okay, I will pick up the index. Right? Now, can I say this is for the current, and the sum from index minus 2 to 0 will be given by this recurrence. So this plus this will be the sum that you will get from 0 till index, the maximum subsequent sum. Make sense? So can I say the last step is return best because you want the maximum sum. So return max of pick and not pick. That's how you do it. But now still there's a question. What if we reach somewhere around index equal to 0? So if you are reaching at index equal to 0 at any moment, that means you have not picked up index equal to 1. Think on this. If you are reaching index equal to 0, that means you haven't picked up index equal to 1. Thereby you are reaching index equal to 0. Right? Because if you would have picked index equal to 1, then index minus 2 would have happened and you would have not reached. So thereby I can say that you have not picked index equal to 1. So can I say the best that I can do is pick this element, because if I haven't picked up index 1, I need to pick it because then only I can maximize my sum. Because remember, the array does not have any negative elements. Thereby I can say I will return whatever there is. Right? But what if index was 1 and you did 1 minus 2 and you went on to a negative index? So you're running out of bounds. So there will be another edge case that you have to think in recursion. So I can say if I'm going index lesser than 0, I will be like return 0 because there will be nothing else. So over here, realize what I did. In the subsequence problem, the only change that I did was I represented it as index. I picked up the element, But instead of going to index minus 1, I just did index minus 2. That's a subtle change that I did in the subsequence problem, because there was a condition which stated no adjacent, right? And there was one base case where I stated if I reach this base case, I'll pick up. And if I cross this base case, there is nothing else to pick up. So there'll be a couple of base cases. We have to think on this. And there's no not pick and pick. So in this way, I have modulated the subsequence code that I've taught you in the lecture 6 in order to write a similar problem with an additional no adjacent constraint. So I hope you have understood the recurrence. It's pretty straightforward. So if you talk about this recurrence, you're going to try out all the possible ways. The time complexity is definitely exponential, which is 2 to the power n, because you'll try out all, like, it's not exactly 2 to the power n, it's going to be lesser than that. So you have to memorize it. Now question arises, how do you optimize recursion? You have to figure out if the recursion has overlapping subproblems. Like if the recursion has overlapping subproblems, then we can definitely memorize it, right? So it will have overlapping subproblems. So what we will do is we'll take a very simple example, 2, 1, 4, 9, and I'll write the index numbers as 0, 1, 2, 3. Let's start from f of 3, where f of 3 basically states is what is the maximum sum you can get if you pick up a subsequence with no adjacent from the index 0 to index 3, which essentially means the entire array. What is the maximum sum if you pick from this? So f of 3 is basically stating, hey, listen, I can definitely pick up. Okay, I can definitely pick up. So if I pick up, I will go to the f of 1. Why? Because if I decide to pick up this particular guy, I cannot pick up this. So I'll go to f of 1 directly. That's perfect. And if I decide not to pick up, I will go to just f of 2. Makes sense. Now, if you are at f of 1, again, there are a couple of conditions. You say, I'm going to pick up. So if you pick up, you're going to go to f of minus 1. And if you decide you're not going to pick up, you're going to go to f of 0. Okay, makes sense. So right over here at f of 1, you have encountered an f of minus 1. So if I try to write this f of 1 in the code, generally f of 1 will look something like this. And this will be calling a pick, right? Which will be, it'll be saying, let's pick this f of 1, which is a of 1. And what's the value of a of 1? Let's see. That's nothing but 1. So let's pick up 1. So it'll be like, let's pick up 1 plus f of minus 1. Now, if you remember, what does f of minus 1 signify? It signifies 0. You remember this? So this guy will be 0. So what I can say is, for f of 1, if you pick up, it will be 1, right? And if I decide to not pick up, it will be 0 plus f of 0, correct? What is f of 0? Whenever you reach f of 0, you're going to pick that element up, correct? Because if you remember at f of 0, what you did? You returned the array of index. So kindly, yes, kindly try to return that array of index, whatever it is. So the first element was 2, so you can return it. So this will be 2. Now the pick gives you 1, the not pick gives you 2, which is the maximum. That's 2. So f of 1 will be 2. F of 1 will be 2. Now a very simple question arises. Yes, a very, very simple question arises. What does this signify? What does f of 1 signify? I told you now, f of 1 signifies the maximum sum that you can gather if you pick up a subsequence with no adjacent elements from 0 to index 1. So if I just take this portion of the array, I can either pick 2 as a subsequence, or I can either pick 1, because there are no other options. Because in this particular array, if I forget this, in this particular array, I can either take 2 as a subsequence or 1 as a subsequence. So thereby, it is very obvious that I got 2, because taking 2 would be a better choice. I hope that makes sense. So I can say f of 1 give you 2. So I can just erase it. So I've erased it. F of 1 is given as 2. Now what will be f of 3? F of 3 will say, okay, I am going to pick. What will I pick? I'll pick a of 3. What's a of 3? That's 9. So I'm going to pick 9 plus f of 1. And I'm going to pick not pick. So 0 plus f of 2. Correct? 0 plus f of 2. I'll have to do this. So there will be a call for f of 2 now. There will be a call for f of 2. So call for f of 2 will now go. Remember this. First f of 1 went and came back with a value 2. So it came back with a value 2. Then f of 2 will go. So now f of 2 will go. Got this? So let's quickly do the f of 2 and then we can wrap this up. So if I have, yes, if I have f of 2, what can I say? I'll either pick it up. So if I pick it up, I'll go to f of 0. And if I decide I'm not going to pick it up, so I'll go to f of 1. Now, do you see an overlapping subproblem? You do see, right? This f of 1 is an overlapping problem. There is no need to again go to f of minus 1, f of 0. There's no need. There is no need. So you can directly take f of 1 right from here because that's the value which has already been stored. So what I can say is in f of 2, if I write the pick will be, I'll pick the a of 2, which is 4 plus f of 0. What will be f of 0? That's this particular element 2. So 4 plus 2 will be 6. So again, makes pretty much sense. If I decide to not pick, then it will be 0 plus f of 1. What's the value of f of 1? 2. So which one will you prefer? The pick or the not pick? I'll be like, I will prefer the pick portion, which is 6. So thereby this value gets as 6. And you can easily get this f of 1 from here, which is 2. Thereby we did not do any further recursions, overlapping sub problems. Got it? Again, what does f of 2 signify? Let's think on this. What does f of 2 signify? The sum between 0 to index 2. The sum between 0 to index 2. So if I take this, again, makes sense. It'll be preferable to take these two elements. That's why you got 6 as the value, because it'll be preferable to take these two guys instead of taking these two, or instead of taking this one, or instead of just taking this, it'll be more preferable to take these two guys, right? That's why you got a value as 6. So at the last moment, whenever you are at f of 3, let me quickly write you this. Whenever you are at f of 3, what will happen? There will be a case of pick, which will say I'll pick f of 3, which will give you a value of 9. And you will say, if I pick, I'll go to f of 1. And if I do not pick, I'll go to f of 2. So f of 2 gave you 6. F of 1 gave you 2. So 9 plus 2 gave you 11. 0 plus 6 gave you 6. So which one will you do? You will directly say this value will be 11. Again, makes sense because you're going to pick this and you're going to pick this. So thereby the answer is 11. And you saw that there were overlapping subproblems, because in order to solve f of 3, we required f of 1 twice, and whatever the answer for f of 1 is computed once, that can be reused because answer will never change for a particular set of array. Correct? That's how we prove that there are overlapping subproblems and how did the recursion work. So now we can easily apply memoization to it, and we can reduce the time complexity, because what will be the memoization technique? Obviously, how many states are there? F of 3, f of 1, f of 2. So can I say there are n states like 0, 1, 2, 3, because there will be f of 0, f of 1, f of 2, f of 3. So there are n states. So you can create an array of size dp of n, and you can initialize that with -1. And then you know the couple of steps. With the couple of steps, over here you say dp of index, and you write one more step over here. If dp of index is not equal to -1, you return dp of index. So if you just write these couple of steps, what will happen is it will change it to a time complexity of big O of n instead of the exponential one, and the space complexity will change to big O of n stack space and a big O of n array space. So that is what the memoization time complexity is still, but there is still a recursion stack space which we have to omit. But before that, let's code this up and submit this. So can I say n will be nothing but nums.size? I definitely can. So let's keep it as that way. And can I say I will return a function which will have initially start from the last index, which is this, and we can definitely carry the nums with that. So we can surely write this, and over here we can write the function which is intf. And can I write int index vector of int, and this will be nums. And what I can definitely do is, if index is equal to 0, we can return 0. If index goes lesser than 0, we can return something as 0. So by the way, if index is 0, please return nums index, because we're going to pick that up. So please do that, and this will be 0. And can I say if I pick the element, remember it's very simple. You either pick, in almost all subsequence problems, it will be always pick or you don't pick. That's as simple as that. And if you pick, you'll go to the next, and this will be this one. And if you not pick, you will basically like 0 plus. If you don't pick, you will simply go to index -1 with the nums. Correct? And at the end of the day, you can say return max of pick and not pick. So if I try to run this, so you see all the test cases running, but if I submit this, you'll get a TLE. So let's quickly have a DP array. So what's a DP? Vector of Java people can easily take some array list or something like that, and -1, and you can just pass on the DP over here. And over here, what you'll do is you'll say vector of int, and you can say int DP. So just make sure you always pass it by reference. Over here DP, over here DP, and what you do over here is step 1 is done, that is passing the DP as -1. Next step is initializing whatever the value of f of index is computed. Next step is if that state is again called, no need to do any further recursion calls. Instead of that, please use the pre-stored value, because we are not going to any further do recursion calls and increase our time complexity. So if I now run this, you will see this running perfectly. And if I submit this, you'll see it is working absolutely fine. So we have learned about the memoization. What is the next step that I generally teach? You guessed it correctly. We're going to learn the tabulation. Yes, we're going to convert the memoization into tabulation. Step 1, declare the DP array of the same size. And you can fill that with zeros or whatever you wish to. So the DP array has been filled up with, let's take the base case. That's how you generally convert memoization, right? So let's assume what's the base case. At index 0, it says a of index. So DP of index, DP of 0 will be of index, correct? So please write it. So can I say the base case will be DP of 0 will be a of 0, because that is what the base case is. Do I have one more base case? I do. Let's see. What is the base case? The base case states if index is lesser than 0, then you have to return 0. So in negative indexes, you have to return 0. So can I say, probably I cannot store this because it's a negative index. So can I store this in a variable where I say negative is equal to 0? Like negative is 0 basically. Whenever there is a negative index encountered, I'll add 0. Just for understanding purpose. So both the base cases have been assigned. Now let's look at the next portion. What's the next portion? Where does if index is passed on 0, it stops over here. If index is passed on 1, it goes. If index is passed on 2, it goes. So you know this, that what is tabulation? Tabulation, by repetition, I've been saying it is bottom up. So from bottom to up. What is the base case? Is 0. So from 0 you'll start building. So 0 you've built, so you'll start from 1. So quickly start from 1 and you can go on till n I plus plus, correct? Now what is the take case? Let's write the take case. What is the take case? Take case is saying I'll take the array of index. That is what they have written in the recursion. And they were saying f of index minus 2. And I've told you, instead of f, you'll write dp of I minus 2. Let's come to this edge cases I'll come across afterwards. We will write this. What about the non-take case? The non-take case will be 0 plus dp of just the previous one. And dp of I will be max of take and non-take. Do you agree with me? You have to. There's absolutely no other option, right? So everyone has agreed with this. Now I see an edge case. What is the edge case? The edge case states if dp like I minus 2, for an example, whenever I is 1, so 1 minus 2, this will go to a negative index. And the case of f of minus 1, you remember there was a case of f of minus 1 in the recursion tree. If I take you slowly, there was a case of f of minus 1 over here, right? So that case will be encountered. So can I say probably I can write something like this. Like, what is the negative? The negative is 0. So if it goes to negative, then only this portion will be there, because this will be plus 0 if it's a negative. And if it is not, then I add up this. So can I say something like this? Right? Can I say if I is greater than 1, then take plus equal to dp of I minus 2. If it is like you're allowed to add this, because that will always be there. But if it is I equal to 1, then there will be addition of 0, so it stays as it is. And if I exceeds like I is 2, then you have to add this with this, so it automatically performs. So can I just add this line up? So just add it only if it exceeds. So if you now do this, this will be the tabulated form. Yes, this will be the tabulated form. And if I ask you the time complexity now, big O of n, space complexity, just a big O of n, no auxiliary stack space. That's the time complexity and the space complexity for this particular tabulation code. And I hope it was as simple as it could have been. What's the next step that I generally do? Come on, guys. This is something which none of the creators does, which is space optimization. कोई नहीं करता यार ये, तुम देख लो पूरा YouTube में छान मार के देख लो. If anyone teaches you space optimization, anyone, you can come and tell me. Everyone teaches you memoization. Some will teach you memoization. Some will teach memoization plus tabulation, and some will teach you some patterns. But over here, you get everything, including space optimization, which is the ultimate form of DP. Like, if you don't do space optimization, you don't know DP. As simple as that. Like, तो फिर तुम सिर्फ हाँ patterns रट रहे हो. If you're understanding how to do space optimization, you are actually understanding DP in depth. That last two states lag raha hai, and so on and so on. Okay, so let's analyze over here. In order to compute DP of I, what am I requiring? I'm requiring a DP of I minus 1. And I'm requiring a DP of I minus 2. Point to note. If I put dots again, our famous dots, if I'm computing any I, let's for an example take any I. What am I requiring? I'm requiring I minus 1's value and I minus 2's value. As of now, where are they stored? At DP I minus 2 and DP I minus 1. As of now, they are stored at any particular array. Do I require I minus 3? Array, no baba no. Do I require I minus 4? No baba no. Do you require I minus 5? Array, kyun chahiye re baba? Last ka do. Give me the last two and I will do my job. So I say, hey, you just require last two. So you require just two space. You don't require a huge array, because in order to compute this, you just require these guys. And the moment I plus plus happens and for loop moves ahead to this guy, then you'll be requiring these two guys. And after this, when I moves here, then you'll be requiring these two guys. So if I can somehow carry the last two guys, my job will be done. And that's the trick of space optimization. So what I will say is, okay, instead of storing them in some DP, can I store them in a couple of variables, previous and previous to? I'll be like, yeah, you can. So let's store them now. Who's stopping you? So I will store them into previous and previous to. And I can say this as cur I. What will happen in the next step? I will move here. So this cur I, like the previous I that was used, will become someone's previous now. For this I, now this guy will be the previous now. Yeah. And the previous will become previous too. Yeah. So can I again formulate the same logic that we have used in lecture 2, lecture 3, lecture 4. So previous to will be previous. Previous will be I. With complete proof, I have done the space optimization. So can I do this now? Can I say instead of this, probably I can keep previous. Now instead of negative, I can keep previous to, because that's what 0 and minus 1 will be. So can I over here write previous to now? I can. Can I over here write something as previous? I can. Can I over here write as take and non-take will be there? Take and non-take will be there. Can I over here write as cur I? I can. Instead of ending over here, I will write previous to becomes previous and previous becomes cur I. That's it. At the end, where will be your answer? Like generically, the answer is at dp of n minus 1. So can I say this for loop ends at whenever I is n. So whenever I is at n, the last n minus 1, where will be the value? Where will be the value? This is I minus 1. Where will be the value? Previous. Yeah. At previous. So you understood how to do a space optimization. Now if I talk about the time complexity, we solved this particular problem in a big O of n and a space complexity of big O of 1. Amazing. Right? So what are you waiting for? Let's quickly code this up. So what do I require? I require a previous for sure, which is a of 0 or nums of 0 over here. I require a previous 2 for sure, which is 0 in this case. and I start from 0. I go on till this, and I say the take will be definitely, by the way, just to make sure you start from 1. So you say it will start from nums of I, take, and you will only take the previous guy if it's a dp of I minus 2, if it's greater than 1. What will be non-take? Non-take will be 0 plus dp of I minus 1, which is previous. Can I say the cur I? Can I say the cur I will be max of take, not take? I can. Now, can I say previous 2 will become previous? I can. I definitely can. There's no doubt in that. And can I say the previous will now become cur I? And at the end of the day, can I say I have to return just the previous, and that will be my answer? Makes sense? So if I just erase this off now, and if I try to run this, you will see this running fine. Here it goes for the summation. Bingo. Works fine. Amazing, right? So if I give a summary of the entire today's lecture, it was, we learned something as subsequence, pick or take or not take, or pick or not pick technique. And then we applied a constraint on that, because we did know about the pick and not pick technique, but we applied an additional constraint and understood how to solve it. After that, we created the tabulation, and we noticed that there was I minus 1 and I minus 2 only being used. Thereby, we converted it into a space optimization. So if you have understood the entire stuff, please, please, please write US. In the previous videos, there was around 7,000 to 8,000 views. There's hardly 80-90 people writing US. So please, yeah, I request you to write US, because it does take a lot of effort. It does takes a lot of effort to make these kind of videos. And if you don't support, how will I maintain consistency, right? So please, please do write. Even if you're watching it after the DP series has been completed, still make a point that you write US. Because whenever I see people writing US, that motivates me that, okay, I'm teaching and people are understanding. And yeah, just do not forget to like this video. Yeah, please do subscribe to us, because I do put very genuine content on this channel. And with this, let's wrap up this video and meet in the next one. Till then, bye bye.
Whenever your heart is broken,